All right, AP Physics 2. It's time to start talking about circuits. So we're going to jump into this real quick here. We just are wrapping up electrostatics. So we talked about building up of a charge and what it means to have a charge build up in one place. It's time to start talking about what happens when we direct that charge. And let's jump right into it. So when we start directing a charge, we get something called a current. And an electric current is the net movement of electric charges. So again, instead of just building up in a field around an object, they're going to move somehow. And we'll get more into that as we keep going here. But that movement is called an electric current, and it's measured in amperes. And it's the flow through a closed path within a circuit. So we'll have to define circuits here as well. And we're going to make sure we talk about all the new language that comes along with this. So first things, voltage difference. We talked about potential difference in electrostatics, and so we know what that is to some degree, measured in volts. But voltage difference, potential difference, voltage, all the same thing. This is the ability to move an electric charge through a resistance. It is the push that drives this current. And we're going to make some similarities and some comparisons to water flowing and things like that coming up that will help you understand how all this works. But a good way to think about this is the driving force behind a current. All right, the voltage difference measured in volts, and then increasing the voltage difference in a circuit will cause more current to flow. So more push, more current goes there. And a DC circuit, a direct current circuit, which is what we're going to be talking about in here, not an alternating current circuit. So real briefly here, a direct current circuit would be something that has like a battery, AA, AAA battery, something like that. An alternating current circuit would be something that you would plug into the wall where you have an AC current versus a DC current. We handle DC current in this class right now. All right, so it needs that current to push through a resistor. Voltage sources are basically batteries. Oops, apologies. So this is something that turns chemical energy into electrical energy. There's some deterioration of the metal in the different cells that happen within here that is collected and moves out of the positive terminal and back into the negative terminal. So this is what can provide a voltage difference, and this is why you've heard of batteries referred to as 9-volt batteries or whatever else they might be, 1.5-volt batteries. Is because that's what provides that push that allows this to move through a circuit. Now, we hear the term resistance that goes along with this, and we think like it's resisting. We're going to fix Mr. Barry's typo as we keep doing this too. It's resisting some sort of movement here, but by resistance, we really also mean anything that we plug in that we want to use electricity. So you see the example right here of the light bulb. The light bulb would be considered a resistor when plugged into a circuit, even though it's really the purpose of a resistor. What happens is the flow of electricity, that current that is pushed by the voltage, gets to something that's going to use the current to perform a certain task, and that resists this flow. It slows it down, and it resists it because it takes some of that chemical potential energy that was transferred to electrical energy and produces something else with it. In the case of a light bulb, it produces heat. Well, more specifically, ideally, it produces light, but an old light bulb like this also produces heat, whereas newer light bulbs produce less heat and more light, and that's why they're more efficient. So R, the resistance, is measured in ohms, OHMS, and we're going to see that symbol as this omega. Okay, so capital O from the Greek alphabet, omega, that's ohms, the measurement of resistance. This changes electrical energy. Again, it's a thermal energy and light in this case. In other cases, it does other things, but the big output typically is from electrical devices is either movement, if you've got like a kitchen appliance, it is light, and to some degree heat, but we're getting much more efficient with those things. So light in terms of your computer screen, in terms of a television, in terms of a light bulb, all of those things producing light. You could also have some thermal energy produced in the case of like a toaster oven or your oven at home or the burners on top, electrical burners on top of your stove, things like that. Insulators are going to have more resistance than conductors. We've talked about this. Now, this last one here, as we put together the wires that make up circuits, and we're going to talk a lot more about drawing circuits and what that looks like and everything else, but some things to keep in mind here as we talk about the resistance that's inherent with this. Thinner wires have more resistance, okay? And that seems odd, but that's because if we have all of this current and we want to push it through a tiny little wire, All right, so we generate a big current with a big voltage. We want to push it through a tiny little wire, then it's hard to push it through, so we have more resistance present there. Longer wires have more resistance just because it moves through more material. The current moves through more material and thus has more resistance associated with it. And hotter wires have more resistance because they've already got that thermal energy, and that makes it difficult to transfer other types of energy through the wires. Now, this resistance can actually be calculated within wires here, right? So many factors affect how that works through the wire here. Again, longer, thinner, and it's because the material has a lot to do with this as well. But you see the thinner, the cross-sectional area there, that's how we're going to calculate that. You see the length, L, and then the resistivity is going to be based on the material that the wires are made of. In most cases, or I'll say in most ideal cases, not all, there's actually some metals that are better, but copper is the main resistor that we use to create circuits and wiring with, and that's because of its general properties. It conducts well, it's malleable, it's flexible, we can bend it, we can form it to the shape that we want, but there are some resistivities that are higher than copper, and you see the main one right here being silver, just over where copper is at, but gold also being right up there with it. Now, we use copper because it's in that same range and just slightly behind silver, and silver is more rare and thus more valuable, and I think we all know that. So you see the resistivity of common materials here, and this will affect the efficiency of a circuit and how well it conducts electricity. We are certainly not trying to make circuits out of things like human skin, but you do see that there is some resistivity there, and so current will flow through people, and that's generally bad. A couple things real quick. I got a couple practice problems here for us. So looking back at this resistivity and wires, I've put a couple practice problems in there for you all to run through real quick if you want to do that quickly. Yes, there are some interesting units. Our bananas are a little weird here, but I don't even have the solutions posted. These are pretty simple. We can address much more of this once we get to class time. Now, all of this comes together to form this thing known as Ohm's law. This is the relationship between the three different items that we've spoken about already. The voltage source, which gives a push to a current, I current there in amps, and it pushes them through a resistance. So now we're going to do our comparison real quick to water flowing. And since we hear I is current, I think that makes a lot of sense, okay? So what you can have in terms of very small circuit, all right, is like a little stream. We're going to think about a little stream as being a small volume of water and thus a small current. Gravity is what's going to pull that stream down, and so gravity would be like the voltage difference. It's going to be like what is driving the movement of a stream as it flows downwards there, and the resistance is going to be anything that it runs over. Okay, like the rocks, whatever other materials might be falling into this little creek. And as we've got a small creek, we've got a little current. It only needs a little bit of gravity to drive it. And the resistance factors are going to be more impactful on the current as it flows because there is less of a current moving there. Okay, so in terms of that, what I want to specify there is a small current with a small voltage source will provide, a small circuit with a small voltage source, like let's say 2 AA batteries, is going to provide a small current, and so it can only move through smaller resistive items. So little things that you would plug into a very small, like the buttons on a remote control, something like that. Whereas if we have a much larger voltage source and we up that voltage from, let's say, 3 volts to 100 volts, now we're going to drive a larger current through. And so we've gone from a little stream to a good-sized river here. Gravity is having to do more to pull it down, so we need a larger voltage source to pull a larger current, and it can move through more material now. So the riverbed's going to be bigger, it's going to be wider, it's going to be deeper, it's going to flow right over those same rocks that held the stream up to some degree with no issue at this point, okay? So we see kind of how this is, as we scale up in voltage source, we're going to have bigger, larger amounts of current moving through, and thus it can move through larger resistors with less issue. As we apply Ohm's law, we see an example right here. This is a circuit diagram, and we're going to get a lot more into what those are too in just a minute here. But we see a circuit diagram where we have a current moving out of a positive terminal, up and through a resistor, and then back around to the negative terminal, okay? And it would continue to flow here. So if we had a resistance of 9.6 ohms right there, plugged into an electrical outlet with a voltage difference down here, our voltage source, our potential difference of 120 volts, we could determine the current flowing flowing through that, and that's 12.5 amps, and that is very, very dangerous. 12.5 amps is easily enough to kill a person, so we don't want to do that, and this is why we don't plug smaller things into large voltage sources, okay? Most of them are designed for specific voltage sources, and this would be a resistance. 9.6 ohms is not nearly enough of a resistance for an iron anyway, so that should actually be much greater. Now, electrical power. The power generated by electricity is going to be measured in watts, just like all power that we've talked about so far. And this is going to be determined by the current present and the voltage produced. In this case, when we're talking about the power of electricity that's being produced, we're not worried about what it's running through right now. We don't care what the resistance is, what the resistors plugged into it are. We just care about the potential difference, what's pushing it, and how much current is being pushed. So you see VI there. Now, what's been done to some degree is there's some substitutions here also. So you got V squared over R and I squared R also. These are other ways to measure power. And so some derivations have been done using Ohm's law and some of these other equations to plug all this in and try to get all that to work so that you could solve for it and by means other than just voltage and current. But what's very important is that you realize voltage and current are the true way that we determine watts here overall. So volts times amps are equivalent to watts. And we'll obviously talk much more about that. Electrical energy that we see over here on the right is not necessarily a common unit in terms of physics, but it's become a very, very common unit in terms of measuring electrical energy usage, or I should say usage of electricity as a whole, okay? What happened was we had things like electricity flowing to houses, and the electric companies need to find some way to bill people for it, rightfully so. If you're going to want to use this, you got to pay for it, right? And so what they did was they said, okay, it's not just a matter of like how much you're pulling at once, because then you could just jump everything up really high, and not knowing how long it went, we couldn't really measure how much electrical current usage was being withstood over long periods of time. So instead, we're taking the power here that we've got, the electrical power that's being used throughout whatever amount of time it's being used for. So this kilowatt hours, it's a very, very weird unit, but is the standard used for measuring electrical usage in homes and buildings and wherever somebody might be paying for electrical energy. Okay, so that is a common unit, kilowatt hours. It's unusual in terms of what it is, but the importance there being, right, you can't run a light bulb for an hour and a big screen TV for an hour and expect to pay the same electrical bill. The power generated by the two are going to be very different, and thus the electrical energy used by the two will be very different as well. This is why you turn your devices off at night. All right, circuits. Time to talk about how we're going to draw some circuit diagrams. These are the very, very, very basic, most basic different types of circuits, symbols that we're going to end up using. There are hundreds of different ones, but these are the ones we have to make sure we know, okay? So a cell and a battery are going to be our voltage sources there, and you're going to see alternating big and small lines. The bigger line typically standing for the positive end, not typically. The bigger line standing for the positive side of a battery, and the smaller line for the negative side. A switch here shown as open, whereas if that were to be pushed down, it would be drawn just as a straight wire. And so obviously these lines here, the line that goes through a voltmeter, that goes through an ammeter, just the straight lines there are going to be our wires. And as soon as that switch closes, then we've got a completed circuit and electricity can flow through it. This basically right here is like you turn the lights off in a room, and so you have an open circuit, which means electricity cannot flow through it. And that's why this switch is shown like that. If you were to push this piece down, like flipping a switch, then you would close the circuit, and now we have the chance for electricity to flow through. So open circuit doesn't work, closed circuit does work. Voltmeter and ammeter, these are two things here we're going to use to measure the voltage and the current in circuits as they go. Resistor and variable resistor here, this is what we're going to use to mark whatever is within a circuit. Lamp technically is what we would use also. It's a different symbol for like a light bulb or a fluorescent light in a room or something like that. But we're almost exclusively going to use just this little squiggly line here for resistors when we show our circuits. And so let's see a transition from one to the other. So You've got on the left right here a drawing of a circuit. But what happened was, as we build things that are more than 3 batteries and 3 light bulbs, like an entire classroom like I'm standing in now, or your bedroom at home, or your house as a whole, or this entire school building, this became too cumbersome to try to draw all of those different items in the same space. So it's been simplified to what you see over here. So we've got our 3 batteries, 2 lines for each, positive and negative ends, our lines depicting the wiring that's connecting all of this, and then our squiggly lines here that show each of the different light bulbs. So this and that are the same thing, but they're both showing, again, the flow of electricity, the point being, though, that this one is more simplified, and so when we get to the point that we scale out further and further and further, and we have very large things that we're drawing these circuit diagrams for, it's much easier to understand. All right, a few types of circuits we need to talk about. First is our series circuit. Series circuit provides one path through which electricity can flow. So we've got a switch here, we've got a battery, current's going to move this way, pushed out of our positive, and flow through the circuit here, and then back to the negative. And this flow is continuous. So it would be more like this. It doesn't make the trip once. It continuously makes the trip and fills it. If we open the switch, it can no longer travel through there and the light bulbs go off. But so long as this is closed, it moves continuously. So one path through which, for which electricity can flow, the current can flow. And so we have a series circuit. Now, in this case, the resistance within this circuit is going to be the sum of the resistors that are there. So if each one of these, let's say, was 5 ohms of resistance, then my total resistance that this current that flows through needs to move through is 15 ohms. 15 ohms here, and then let's say I've got a 9-volt battery. Now using Ohm's law, I can determine what the current flowing through it all is. So these are some of the calculations we'll see coming up. The voltage, the total voltage here is equal to the voltage sources. Okay, so if I went from one 9-volt battery to 2 9-volt batteries, I have 18 volts total of potential difference that's going to push the current through this circuit. Now, the voltage drop is the voltage used at each resistor to push the current through that resistor. All right, so let's say we're going to go 3 ohms each for these resistors and a 9-volt battery. As I move up here, it's going to take some of that 9 volts to push this current through the resistor because it's a resistor. It's resisting the current. The current doesn't want to naturally flow through it, okay? So the voltage source needs to be strong enough to push the current through it. That happens at each of these locations. At each spot, I'm going to lose some of my overall voltage that's produced by the batteries as it pushes the current through the resistor. So if each one of these is 3, and I made those numbers very even on purpose here, then I'm going to go right here, I'm going to have 9 volts. It's going to take 3 volts to push the current through this, and so I'm only going to have 6 volts left here. 3 more to push through this one, only 3 left here, 3 more to push through that one, and I'm down to a count of 0 volts at this spot in the circuit. But as it gets back to the battery, this replenishes that potential difference and pushes it back out again. As you come into the negative terminal of a battery in all circuits, you will have 0 volts of potential difference left. Okay? That's important because it uses the push that's generated by the battery to move the current through each of the resistors as it goes around. Now, if I take one of these resistors out and I go from having 3 volts and 3 volts and 3 volts, I still have those 9 volts. So now it's going to push through this resistor with 4.5 and this one with 4.5 so that the total is still 9 and it still gets back to 0 as opposed to pushing through each one with 3. In terms of these being light bulbs, what that's going to do is it's going to make the light bulbs brighter. That's really what it comes down to. Okay? It's going to make the light bulbs brighter. It might change the current and everything else based on the proportions of Ohm's law, but we still have to get back to a voltage of 0 before we get to the back to the battery. So if I take one more bulb out, the whole 9 volts is used in just one light bulb right here, and I'd have an even brighter bulb. And hopefully that makes sense, right? If I have 3 bulbs and I keep the same battery, as I take one out, the other ones are going to get brighter, and that's just how that's going to work. All right, at least in a series circuit. So now let's jump into a parallel circuit. This is a circuit through which there is more than one path for electricity to flow. Okay, so right here we've got our battery, and we're going to have our potential difference. The longer line is going to be the positive end, so my current is going to move out here, and it's all together, all together, all together, and then we get to this junction right here, and some of the current's going to flow through there, and some's going to flow down here. And think about it like flowing water through the bed of like a river or a creek. As water were to flow, it's all flowing together, and as it gets here, some would flow that way and some would flow this way. And then it's going to go down and around and come back and meet here where this part went through, and now we're going to have it all back together as it moves up into back to this terminal and as it continues to push through everything. Okay? Now in this case, the voltage drop in a parallel circuit is going to be the same across all of the resistors, because the push here is going to push and push and push that current until it gets to here. And so the same push will be applied through both of these channels, because the push leading up to it is going to be evenly moved through both channels as it's distributed and as the current is distributed through the different spots. So in this case, the voltage drop, the amount of push needed to move the current through those resistors, is going to be the same through both channels. Now the resistance is going to be much more difficult to figure out what's going on here. All right, these are parallel circuits are much more efficient in terms of like percentage of energy lost in certain areas and things like that. So our resistance in a parallel circuit can't just be adding them all up, because they don't all restrict all of the flow, all of the current as it moves through the circuit. Instead, we add the reciprocals up. So 1 over R1, if these are my 3 resistors, and I've got a current flowing through here, so some goes there, the remainder goes here, they all flow through and meet back up to head back this way, right? The total resistance of these 3, R total here, is going to be 1 over each of the others. What this means is the total resistance will always be less than the smallest resistor. The total resistance will always be less than the smallest resistor. This makes parallel circuits crazy efficient in comparison to series circuits. And we use these mostly when we are developing circuits at this point in time. Now, we use kind of a combination, but we'll get to that in just a sec here. The current, as we go through here, okay? Reminder, the current splits through the different channels. So again, we've got a battery, it's pushing out here. The current at A1 is the whole current. All of it is still there. But then some of it's going to flow through this resistor in this branch, some through there, some through there. So A2 and A3 and A4 are going to be fractions of the total current that flowed out of the battery. All right? That means then that the piece that's here plus the piece that's here plus the piece that's there will equal the total that went into these currents. I can't say flowed again. I don't know why, but that sounds awful. And then they'll come back together, and back here, right where my cursor is right now, you would have the total current again, same as A1. But when it's broken through these different paths, think about it like a river that's flowing and it has some tributaries, but then they all come back together at the end. That's what we're looking at here. All right, so we've still got our flow, we've still got our current, they just come back together there at the end. So a couple examples for us right here. We see a 9 amp current move out. We're saying current splits 3 ways. We're going to make the assumption here that we have the same resistor in the middle for each, so we've got a current of 3 amps moving through each one. And so in this right here, 0.3, now we might have spots where we have different resistors. So the one we look at right down here, this is the same as what we looked at a second ago. 0.3 divides evenly because let's say each one of these is an identical light bulb, something like that. And so it comes back. In the case here, which is much more realistic, maybe what this is like a surge protector, something like that, right? Where you have 3 different devices plugged in. Well, the total current is still going to add up to what we had before. So you see we get 0.2 and then 0.3. It's just broken in different values as it moves through and then comes back together here. So it really depends on what you're putting into these circuits also, not just what the voltage source is. The current's going to be very dependent on both the voltage source and whatever resistors you're putting into a circuit. Now, in reality, these are both very, very simple, and the way that we actually are going to use and create circuits is going to be much more complex than this. So we had to combine them to form, well, we'll get into this coming up here in just a sec, right? Our series parallel circuits. So series circuits, again, put them all together, 20 plus 30 plus 40 is 90. Boom, that's our overall resistance in a series circuit there. And then in the parallel, we would do the reciprocals, right? 1 over 5 plus 1 over 14 plus 1 over 21 plus 1 over 25 plus 1 over 100 equals 1 over the total resistance. We would solve for that total resistance. And so to hit our rules again real quick, series circuit rules, I want to hit these a lot to give you the reminders. But series circuit rules, the current is the same throughout because there's only one path. The total voltage generated by the total voltage right here generated by the batteries is going to equal the voltage drop at each resistor. So remember, we had 3 resistors before. Each one dropped its sum. All those together will equal the total voltage. And then the total resistance is just going to be each of the different resistors added together. All right. In a parallel circuit, the current is going to equal the total through each branch. So reminder, each different branch is going to have a different current running through it. The total current is going to be the sum of each of those. The voltage, the push, is going to be the same through each branch because of the way they divide. We just talked about that too. And our resistance is going to be the reciprocals. Now, what really happens is we put those together. So we combine these. So let's say in this case here, I've got a voltage source. I have 2 resistors in parallel and another resistor then outside of that parallel. Okay? What I need to do in this case is analyze these one at a time and then put them together. So I have to use, whenever I'm analyzing using Ohm's law or anything else, the separate rules. I can only apply series to series sections and parallel rules to parallel sections. So my first move here would say, okay, I need to combine 1 and 2 to form a single resistor. We don't actually combine them, but in terms of solving for this circuit, this is what we would do. And then I can treat that as one resistor that's in series with R3. Okay, and you see that right there. We need to calculate R1 and R2 that are parallel and then put them in with R3. So we would find our total here. Yeah, oh, this is once we've combined all of them all together, right? So we'd have our total resistance, 73 ohms. We've got 100 volts put in here, and so we could find our total current. Now, combining these down, I think this is a step worth looking at. I want to go through this one step by step so that you see how these can be combined and simplified in terms of circuits here, okay? So we've got a circuit diagram where there's 2 in parallel here. There's another one in series outside of that. And then within all of those, there's another one in parallel over on this side. So the step-by-step here would be, we need to find the total resistance first, and then we can find the current and blah, 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 whatever else we need to solve for, okay? First thing here is going to be, we're going to find the total resistance. So my first move is going to be to combine those two so that I get one resistor right there. All right, combined via parallel rules, and reminder that you're always going to be smaller. You see right here, 13.2, smaller than the smallest of the individual resistors in a parallel circuit. Then we've got that, now that we've found those, 1 over 28 plus 1 over 25 equals 1 over 13.2. And run that math if you need to, but that's where we're going to be at there. And so now we've got these two that are in series, right? That's the next immediate item that we need to look at. So we combine those by just adding them together because they're in series. And now we have these and one resistor there. And now we have one resistor, and you see how it's marked 1, 2, 4. That means we've combined resistors 1 and 2 and 4. And we have resistor 3, so we'd say 1 over 51.2 plus 1 over 24 is going to give me that total resistance. And you see, because this was largely parallel, that it's only 16.34 ohms. I mean, it's overall much lower resistance than any of these individual resistors, and that's why those parallel circuits are so efficient. But based on the setup and what we want to accomplish, we're still going to utilize some series items at some points within these. All right? So these are the 3 main types in DC and AC circuits. I think that's what we really need to get into. Another quick example here of different ways that you might see some of these different circuits lined up. You've got all series here. You've got all parallel there. This would be a series parallel because you got 2 in parallel and then 1 in series with it. This would also be a series parallel because you got 2 in series and then they are in parallel to this other one over here. All right. So being able to identify those is important in terms of solving. We want to make sure we can do that. All right, to jump into the stuff that's a little more advanced here. First, I'm going to define EMF. Now, I need you to note that those letters are lowercase because next unit, when we get to electromagnetic fields, we're going to have capital EMF, and this is foolish, but it is what it is. So lowercase EMF is an electromotive force. All right, this is a voltage deployed by any source, the battery here, that's the potential for a circuit. We do want to note that it's all lowercase, right? And this is measured in volts. And so we're not going to freak out. This isn't something new. It's another name for whatever it is that generates potential difference, voltage difference, the voltage, whatever. It's what a battery does. That's really what it is. It's defining what a battery does. And we're hitting all of Mr. Berry's typos. Apologies. This is why I don't teach English. So that's what we're looking at there. And as we utilize those, we're going to get into capacitors. Now, we talked about parallel plates and what it means to have a capacitor in our last unit when we did electrostatics. So a quick reminder, and now we're actually going to utilize these within circuits, and you're going to see the reason for creating these, okay? So this is energy storage. This is built into some resistors. This is built into circuits in different spots. This can be very, very well utilized to make sure that we are storing energy where we want to within circuits. So two parallel plates, they start with equal number of free electrons on each side. We build up the difference between them. We've got our dielectric in the middle. That's very important for these because that provides a space for the field to build up there and then be easily utilized as we have different voltage plates on either side. Again, we did this last unit, so quick reminder there. We see this built up, and we see our different plates and our electric field in between as the electrons move back and forth. You see what a capacitor will look like, the two straight lines that are of even length as opposed to ones that are of different size for the plus and minus terminals in a battery. And we see the connecting leads or the wires coming in or out of this. And we saw that here. This is what a lot of them are actually built like within circuits, because as you create a circular shape for these capacitors, you can greatly increase the surface area in between this area with the dielectric and the conductors on either side by just rolling it up. And so a lot of times you'll see these as round when you see them actually utilized within circuits, okay? As opposed to just flat like this. But when we talk about parallel plates, it makes a lot of sense to see them as flat plates like this also. So we're going to kind of utilize both here. But realize if you took this and stretched it out long enough and then rolled it up, you've got the same thing that you saw on the previous slide. The dielectric, this is what is in the middle, all right? This is the material between the plates. Based on whatever material you use for that, there's going to be a different dielectric constant. And what this does is it allows the electrons to pass through between the different plates and thus build up, depending on how much charge you want to build up there, and dissipate once you decide you need to utilize that. And really what it comes down to then is we're storing a charge here the same way that we're giving a voltage source similarly to what we would do in a battery, but a battery is taking chemical energy stored in metal and converting it to electrical energy. This is just storing electrical energy and then utilizing it in the form of a current when necessary. So different dielectric constants based on different materials, right? Don't memorize any of these, right? But you see the constants there, that little odd capital K, and you have a strength in volts per meter associated with them, all right? These allow for that distance between those plates to be minimized if utilized correctly without causing damage to the capacitor. So the materials that a capacitor is made of are very, very, very important. And this is why you'll hear things like lithium-ion battery. And so they'll actually state in a lot of cases the materials that are utilized within these to show that it's a higher or lower level capacitor. And the way I said that also, I said battery, right? These basically function as batteries. What most people consider to be batteries are actually capacitors. They're building up a charge and they're storing the charge, but a true battery is doing chemical to electrical energy transfer, whereas a capacitor is not. So really what it comes down to is most people misstate this. What you recharge in your phone, what you recharge in your laptop, anything that is rechargeable that you plug back in and store more energy in by giving it an electrical input is actually a capacitor and not a battery. Okay? So another student, you can start correcting them. I do this to my wife all the time. She just loves it. But you can start telling people, oh, when they say, oh, my battery's low on my phone. No, it's not. Your capacitor is low. You just need to gather more charge within your capacitor. Yeah, that'll go off real well. Don't actually do that. People don't like it when you do that. All right, calculating capacitance. The amount of capacitance that's in here. We hit this very briefly in the last unit, but it's the charge per volt. Okay, we see coulombs per volts. That is what a farad is. We very briefly mentioned farads in the last unit, but I want to make sure now that we are going a little more in depth there. So this is the SI unit for electrical capacitance. It measures how much charge we can build up between these plates. All right, so capacitance and farads, and we see these equations, and y'all, knowing me, we will have plenty of time to interact with these equations and make sure we can use them. Now, we see an image here of this building up, and we go from A to B to C to D, and we build up as large of a potential difference as we possibly can, because right now we're just starting with two plates here that conduct and thus gather electrons. As we drive a current through this and we build this up, we actually end up separating positives and negatives, and then we move this out. So you unplug your phone, and now we have this buildup to be utilized as is necessary. So I think just seeing the step-by-step, and maybe even pausing this one for a second and reading quickly through those subtitles and stuff like that will be helpful in gathering understanding of exactly what's going on here as we build up a charge. If we've got these capacitors, we're certainly going to put them in circuits, right? So things to look at and how we will utilize these, especially if there's more than one. So if you've got a very big device, or some of the earlier EVs, and I think even some electric vehicles now aren't made with one big battery, with one big capacitor within it. There are several hundred very small ones, so that if one piece is damaged, you just take that piece out, you get a new one, right? So efficiently, it makes a lot of sense, and so you can put them in series or in parallel. We'll look at both of those in a second. But let's say some EV producer for an electric vehicle, right, has generated a new battery. Then instead of having one large battery, has 100 small ones. They need to put those together to utilize all of that energy at once. So they can put it together in series. And in the case here, now we're flipping what we did with resistance earlier. In the case here, capacitors in series are 1 over each of the different capacitors all the way through here. And so this makes for a very efficient overall capacitance as we put all these things together. And so the effective plate separation increases. And so, right, as you can see right here, right, the total capacitance is less than the smallest capacitor value. So that makes it, very inefficient overall. And we're not going to put these in series to a large degree, right? It just doesn't make sense to do that. Apologies, I just switched those. This makes it very inefficient. And so we're not going to put this in this method here, because we're going to lose overall. Like we could put in 100 of these, and whatever the smallest one is, that's the most capacitance we're going to have. Whereas if we put these in parallel, now we're putting them all together. Okay? So what we're doing essentially then is, instead of saying, okay, as it flows through the series here, let's say this one's big, medium, small. Well, as we build up a charge and as it flows through the whole thing, it can only flow through the smallest one as a volume of current at one time. That's the most that could flow through there, right? So essentially, instead of having all of these added together, we've got the smallest surface area dictating everything else that's happening within the circuit. Whereas if we put them in parallel, well, now I've got the surface area of these two, plus the surface area of these two, plus the surface area of these two, and so forth and so on. Now we can add them together, and this is much more effective because we've effectively increased the surface area over which we are storing a charge. As we store energy in these capacitors, okay, this is going to be based on Q and V. Q being our charge and V being our voltage. So very specific amounts of energy. These are stored here. So we're going to use them specifically for electronic circuits and making sure that things are storing a specific amount of energy to use when necessary. In a spot where you may not think of this. So let's say your computer's off. It's not plugged in, it's closed, it's sleeping, whatever. A lot of times there'll be a couple small LEDs that are like red that might still be on, or like blink slowly to show that they're in sleep mode, something like that. The reason that can happen without dissipating the battery, the capacitor, or without being plugged in, is because near that bulb, a little capacitor is part of the circuit. It stores up enough charge to continue to run that battery for an extended period of time, even though the computer is not fully functioning. So this is one of those like little pieces within a larger circuit that might utilize a capacitor here. And again, you see our electrical energy storage here within a capacitor, and we will talk a lot more about this these equations as well as we move through this unit. So Kirchoff is the last thing we need to talk about here, and I am positive I am mispronouncing that, so apologies to Kirchoff, but I'm going to stay with using it one way there, and if I'm wrong, I'm wrong. What we're looking at now is a circuit where we have more than one voltage source. Okay, so these rules govern the conservation of charge and energy in electric circuits once we have more than one potential difference source, more than one source of the push that drives these circuits. Okay, so it analyzes more complex circuits, and this is typically, again, involving multiple voltage sources. So a case like right here. First, the junction rule. There's two rules we're going to look at, okay? The junction rule is our first one right here. And this states that the sum of all currents entering a junction must equal the sum of all currents exiting the junction. A good way to think about this, how did I misspell of? What? Get out of here. Nope, that's why. A good way to think about this is conservation of charge. All right, if I have 10 amps going in here, I can't have 4 and 4 amps leaving. Where do the other two go, right? The current doesn't just disappear, just like all things in physics don't just appear or disappear. They just change. In this case here, they're changing direction for the current. So we would have this total current here split between 2 and 3. They must be equal overall. Now, that one seems probably really, really straightforward, but we still have to state that we have this conservation of current in this junction rule because we'll utilize that a lot later. Now, the next one is the loop rule. Okay? The loop rule. This one gets a lot tougher. This says the sum of the voltages in a closed circuit, so one loop within this overall circuit. We got two loops here, one here, one there, and then we actually could do one around the outside as well, okay? It says that they are going to go back to zero in the same way as the voltage and the voltage drops went from the total voltage down to zero in the previous circuits that we looked at. What this really means is that's going to be applied and hold true for each different loop that could be present. So again, this top piece right here could be one loop. This bottom piece right here could be another loop. And then if we were to take out this middle line, the outside could be another loop. Any potential path through which current can flow is going to be considered a loop in this case. Now, right now, this seems like chaos, but we will do a lot more with this coming up, I promise. As we apply these rules, a few things we need to do, and I'm actually going to read from slides here, okay? We need to assume all voltage sources and resistances are given, all right? Everything that's given to us, we're going to label. If we don't know it, that's probably what we're going to be solving for. And so we will label voltage sources as V1, V2, resistance sources as R1, R2. But if we know what they are, like if we knew what R3 was, we're going to label that as whatever the resistance is as opposed to just R3. We're going to label each branch with a branch current, I1, I2, I3. So each different branch, we're going to mark the current in it as we do this. We're going to then apply the junction rule at each node, a node being a spot where the difference in current, there could be a difference in current on either side. So this right here is a node because you got I1 going in and then I2 and I3 coming out. Okay, so that's what defines a node. This corner right here, not a node because it's the same current as it moves through either way. This right here is a node because you have a split in the current. So it's a spot where the current splits. Then we're going to apply the loop rule for each of the independent loops in the circuit, and we're going to solve the equations by substitution and or linear manipulation. We're back to our algebra here. And you see, we've defined these loops overall, and this is what will allow us to solve for this. And once we have all of these different things together, we can do some substituting and so forth and so on to make all this work. So that's how our procedure for applying this. This is something we're going to want to note, and this is going to be kind of our problem-solving procedure for this unit. That's really important. An example here, we've got 1, 2, 3 different loops, okay? I'm going to jump to this next one and just show you the example quickly so that we can build on this much more in class as opposed to saying, hey, pause and try to solve for this because this is going to be pretty tough. But you see right here in loop 1, we have some current I1 right there that's moving through resistor R1 and R3. It's generated likely because of this voltage source, right? In loop 2, we have a current I2 moving through R2 and R3. Now, what we need to realize is as they both move through R3, we've got a different current right there, I3, coming out of that space, all right? And then overall for this one right here, we've got a current that's moving through both voltage sources around the outside and then through R1 and R2, but not through R3. So that's a lot going on right there. So let's look and see what's going on. So we have node A, node B, and all these 3 different loops that could be moving around here. So 2 nodes, again, A and B, as we see right there. 3 loops, 1, 2, 3, we just defined all those, but only 2 of the loops are independent and thus can have the loop rule applied. And so 1 and 2 are the only ones that we can actually apply the loop rule for. We can't do that around the outside because it's not its own independent loop. It overlaps the other loops. That's important. So node A, we've got I1 and I2 going into it and I3 coming out, right? And node B, we've got the opposite. I3 going in, and 1 and 2 going out. For loop 1, we're going to put all this together, okay? We know that the voltage drop must get back to 0 in the end, and that's why you see equals 0 for both of these. What I've got is 10 volts here, pushing upwards for loop 1 as it moves around, 10 volts right there. Then I1 is the current running through R1, right? And then it moves to A and goes down. And so now I have I3, because that's the combination right there. I3, that's the combination of I1 and I2, as stated up here, as it moves through R3, and then it comes back around and will be 0 right before it gets back to that source. The same thing with 2, 20, and then I2 moves through R2, gets to A. I3 moves through R3, gets to B, and then it comes back to its source also at 0. And we see this term being the same between the 2 here, and that's what's going to help with our problem solving. So we see a solution right here. I'm substituting different parts in, and I'm saying things like I3 equals I1 plus I2. I'm subbing in items that I found earlier, right? I3 then, I put that in here for this, and I substitute and so forth and so on, and I can get all the way down here to having 2 equations and 2 unknowns. And as soon as I have as many equations as I have as unknowns, then algebraically we can solve the problem. And that's really the big thing with this. Kirchoff is going to give us additional tools by which to do some substitution, and that's what we really care about here. All right? So, an RC circuit is a resistor and capacitor circuit. It contains at least one resistor and at least one capacitor. I've referred to DC and RC circuits so far. DC is just going to be a direct current circuit, okay, where we've got a battery source. And then RC is going to be as soon as we add a capacitor into that. They're initially uncharged, and they will charge as a current runs through the circuit. So when you put, let's say, a new device, you get a new device, there's no charge on the battery for it and the capacitor for like a new phone, you plug it into the wall to charge for the first time, right? It doesn't have a charge until you build that charge up, and that's what we're talking about here. So they're initially uncharged, and they do charge as a current runs through the circuit. The capacitance is the amount of charge that's stored there. We think about that in terms of that little green battery sign and a percentage on a phone, but that's really what's happening. It's charging something as it builds up there. So lower resistance in the circuit will cause it to charge quicker. So the last thing I want to look at is charging and discharging rates. And you've probably noticed this as you plugged capacitors in before, as you plugged your phone in. As it charges, it quickly, like let's say it's close to 0, it's going to quickly build up charge for a while as it starts to cover the plates and starts to fill that space in between the 2 different plates. And so it will do this quickly to start, and then it will level off as it reaches its maximum capacitance. And this is because that surface area is largely filled at that point, and so you're just kind of filling in the little gaps that are left, whereas when they're blank and empty, it's very easy to fill in between there. The same thing will happen there as discharging happens as well. Now, the good thing about this, as far as our calculations in AP Physics 1 and 2 specifically right now, obviously, is we are algebra-based. And so a lot of the descriptions for the actual charging rates are described via calculus, as you see with the curved lines, but we will still do a little bit with that, so be prepared for that. And so that's the end here. I'm excited to get into these. Building circuits is usually pretty fun, so I will see you in class.